All right, so today we're going to deep dive into something that almost sounds like science fiction.
Oh, yeah.
Using viruses to make antibiotics effective again.
Yeah.
You heard that right, like reversing antibiotic resistance, almost like hitting a rewind button on this global health crisis.
Yeah. It's a pretty radical
It
concept
is.
when you consider that almost 5 million deaths globally were linked to antibiotic-resistant bacteria just in 2019 alone.
Yeah, that's a scary statistic.
It is, and it's only getting worse,
Right.
but this new research offers a potential solution.
It's really interesting. So where do viruses fit into all of this?
Well,
We're talking about bacteriophages, right?
exactly.
Those viruses that infect and kill bacteria.
Exactly. Phages have actually been around for much longer than antibiotics.
Oh, wow.
They were even used to treat infections before penicillin hit the scene.
Really?
Yeah, now researchers are looking at them in a whole new light.
Okay.
Not just to kill bacteria directly,
Uh-huh.
but to manipulate them into becoming vulnerable to our existing antibiotics again.
Okay, so before we get to that, let's quickly recap how antibiotic resistance even develops in the first place.
Sure.
I know you've probably heard about superbugs.
Yeah.
But how do they actually become so resistant?
So one of their most effective weapons is something called an efflux pump.
Okay.
Think of it like a revolving door on a bacteria cell.
Okay.
The antibiotic tries to get in, but the pump just spins it right back out before it can do any damage.
So the bacteria have essentially built themselves like an impenetrable fortress.
Exactly.
No wonder our antibiotics are struggling.
Exactly, and that's why we see those scary headlines about infections caused by Pseudomonas E. coli Klebsiella.
Yeah.
All bacteria that have become resistant to multiple antibiotics,
Right.
they're the heavy hitters on the World Health Organization's list of major threats.
Wow. Okay, so back to the phages.
Right.
How are scientists using them to outsmart these superbugs?
Well, researchers realized that some phages actually use those same influx pumps to their advantage.
Oh, interesting.
Imagine a Trojan horse sneaking into a city, disguised as a friendly delivery.
Okay.
That's essentially what these phages do. They latch onto the efflux pump and inject their genetic material right into the bacteria.
So the bacteria's defense mechanism becomes its weakness.
It does.
That's a pretty clever twist.
It is, and that's where the idea of phage steering comes in.
Okay.
Researchers like Paul Turner at Yale are using this knowledge to force bacteria into an evolutionary corner.
A corner?
Yeah.
What do you mean?
Think of it this way. To survive the phage attack, the bacteria have to evolve.
Uh-huh.
But the changes they make to resist the phage often make them lose their antibiotic resistance.
Oh, wow.
It's like a burglar disabling a security camera only to trip an alarm in the process.
Oh.
They solve one problem but create another.
So it's not just about using phages to directly kill the bacteria. It's about using them to make the bacteria vulnerable again.
Exactly.
Like resetting the game.
Exactly. And Turner's research has shown some really promising results. They found a phage called OMK01 that targets a specific efflux pump in Pseudomonas aeruginosa, one of those superbugs we talked about.
Right.
When they exposed the bacteria to this phage in a lab setting,
Yeah.
the bacteria evolved to resist it.
Mm-hmm.
But in doing so, they lost their resistance to 4 different antibiotics.
So it actually worked.
It did, and there have been similar results with other superbugs like Acinetobacter baumannii.
Wow.
So we're still in the early stages.
Yeah.
But the potential of phage steering is enormous.
That is incredible.
Yeah. So very promising.
It is. So that is some seriously encouraging news.
Yeah.
But I know it can't be all smooth sailing.
Right.
What are some of the challenges that come with actually using phages in this way?
Well, you've got to remember that bacteria are incredibly diverse.
Right.
And each phage is very specific
Okay.
to the bacteria it infects. So it's not a one-size-fits-all solution.
So it's not as simple as just grabbing any old phage and throwing it at an infection.
Right.
It's more like finding a needle in a haystack.
And adding another layer of complexity.
Okay.
Bacteria are masters of adaptation.
Right.
What worked yesterday might not work tomorrow.
Yeah.
They're constantly evolving, which means we need to be one step ahead.
So this isn't a cure-all. It's an ongoing process of discovery and adaptation.
It is.
Sounds like it could be pretty resource-intensive.
It definitely can be.
Yeah.
First, you need to identify the specific bacteria causing the infection.
Right.
Then you have to isolate and characterize potential phages,
Okay.
looking for that perfect match.
Yeah.
It's a meticulous process, but the payoff could be huge.
It's like playing a high-stakes game of microbial chess.
Yeah,
But beyond the complexity of actually finding the right phage,
right.
you also mentioned potential risks.
Yeah, one of the biggest concerns with phage therapy is the possibility of triggering a severe immune response,
Oh, okay.
like septic shock.
Okay.
You see, when phages kill bacteria, they release all sorts of internal components.
Right.
This isn't usually a problem.
Okay.
But if it happens too quickly or on a large scale, It can trigger a massive inflammatory response.
So it's like a double-edged sword. We want the phages to be effective,
Yeah.
but not so effective that they cause more harm than good.
Exactly. That's why researchers are looking into ways to mitigate these risks.
Okay.
They're exploring everything from carefully selecting phages that kill bacteria more slowly to engineering phages that are less likely to trigger an inflammatory response.
Okay, so we've got this incredibly promising new approach, but it's complex.
Right.
It requires a lot of research, and there are potential risks to consider.
Yeah.
Where does that leave us in terms of real-world applications?
Well, there have been some remarkable case studies using personalized phage therapy.
Oh, okay.
These are situations where doctors have been able to identify the specific bacteria causing an infection
Right.
and find a matching phage to treat it.
So like a tailor-made treatment
Exactly.
for a specific bacterian infection. Sounds very personalized.
There was one incredible case of a patient who was in a coma with a multi-drug resistant infection.
Wow.
Nothing was working.
Oh, no.
But after receiving phage therapy, the patient woke up
Wow.
and started responding to antibiotics that had been completely ineffective before.
That's incredible. So this isn't just a theory. This has actually saved our lives.
It is, but we're still very much in the early stages.
Right.
Right now, phage therapy is often considered experimental.
Okay.
And requires special approval on a case-by-case basis.
Yeah, that makes sense.
Which makes sense. We need to be cautious. But this regulatory hurdle can make it difficult to conduct the research we need to move the field forward.
So we need more research to prove the safety and effectiveness of phage therapy.
Right.
But the regulatory process can make that research challenging to do.
It can.
It's a bit of a catch-22.
It is. But even with these challenges,
Yeah.
there's a growing community of researchers who are incredibly passionate about phage therapy and its potential, and for good reason.
Yeah.
We're in a global race against antibiotic resistance, and we need all the tools we can get.
We can't afford to wait around for bacteria to become less resistant. We have to be proactive.
Absolutely. And that's what makes phage therapy so exciting.
Yeah.
It's a completely different way of thinking about how we fight infections.
Right.
We're not just trying to create stronger antibiotics.
Mm-hmm.
We're learning to manipulate bacteria's natural enemies.
So what does the future hold for phage therapy?
Right.
Where do we go from here?
Researchers are focusing on a few key areas.
Okay.
One is standardizing protocols for phage therapy.
Yeah.
Right now, it's very individualized, but having established guidelines would make it much easier to implement and study.
It would take some of that S work out of the process.
Exactly. Another focus is phage engineering.
Okay.
Scientists are learning how to modify phages to make them even more effective.
Oh, wow.
Maybe they can target multiple bacterial strains or deliver additional therapeutic agents.
So we're not just using phages as they exist in nature. We're actually learning how to customize them.
We are.
Kind of like upgrading our weapons. Yeah. It's amazing to think that we might be able to engineer viruses to fight bacteria. Talk about turning the tables.
It really challenges our assumptions, doesn't it?
It does.
We're learning to appreciate the complexity of nature and how these intricate relationships can be harnessed for good. This shift towards understanding and utilizing these relationships is a big part of what makes phage therapy so fascinating.
It's like we're moving away from the idea of simply trying to destroy all bacteria and instead learning to work with them.
Right.
Or at least manipulate them to our advantage.
Precisely. And this brings us to another exciting area of research, the human microbiome.
I've heard about that. It's like an entire ecosystem living inside of us.
It is, and we're only just beginning to understand how important it is for our health.
Right. Okay.
What's interesting is that phages have the potential to play a role in shaping the microbiome in beneficial ways.
So instead of trying to wipe out all bacteria with antibiotics, we could use phages to selectively target the harmful ones while leaving the beneficial ones intact.
That's the idea, and it raises some really interesting questions about the future of medicine.
Yeah.
What if we could use phages not just to treat infections, but also to prevent them in the first place?
Wow.
Could we modulate the microbiome to create a more resilient internal ecosystem that's less susceptible to harmful bacteria?
That's a really mind-blowing concept. It's like using phages to train our immune systems to be more effective.
Exactly, and this is just the tip of the iceberg.
Wow.
We're still in the early stages of exploring the potential of phages, but what we're discovering is incredibly exciting.
It is. So as we wrap up our deep dive into the world of phage therapy,
Yeah.
what's the one thing you hope our listener takes away from this conversation?
I think the most important message is that we're not powerless in the face of antibiotic resistance.
Right.
There are innovative solutions on the horizon, like phage therapy.
Yeah.
And we all have a role to play in slowing down the spread of resistance.
We can all be part of the solution.
Absolutely. This is a story that's still being written.
Yeah.
And we're all contributing to the next chapter.
So listener, we leave you with this thought. What if the key to overcoming antibiotic resistance lies not in creating new drugs, but in harnessing the power of nature itself?
It's a great question.
Keep exploring, keep learning, and stay curious. Thanks for joining us on this incredible journey.